Hello, everyone. Welcome to the TIFR CAM Colloquium. Today, we have the pleasure of having Dan Mikulincer from MIT, who will be telling us about Lipschitz mass transport. Over to you.
Okay, thank you. Okay, thank everyone for coming, and thanks for the invitation. Right, so title right here, Lipschitz mass transport, which is a bit of an ad hoc definition. So what I'll try to do, at least for the first part of the talk, is to explain what I mean by Lipschitz mass transport, and then explain some results and implications. But before I can actually explain what is Lipschitz mass transport, let me start with mass transport. And the story about mass transport is a very nice story with a very rich history. So at least in this form, you can trace it back to the late 1800s in a paper or a note by Gaspard Monge, and he calls it the memoir about Deblay and Remblay. And I'm not very good in French, but Deblay or Remblay is literally a pile of sand you take from the earth, and the other one, probably Remblay, is a hole in a construction site which you need to fill in. Okay, so that's somehow the problem of mass transport Monge cared about. You have a pile of sand, you have a hole in a construction site, and what you need to do, you need to transport the sand from the pile to the construction site, because you want to do construction. And the main problem here is how to do it in an optimal way. Okay, you want to minimize the energy which you need to work with in order to move the sand from the pile to the construction site. Okay, so before I continue, maybe I should mention, so none of those, all of those pictures are artificially generated. So this pile of sand doesn't exist, and this construction site doesn't exist. And actually, and that will be true for all images in my slide, almost all images in my slide. And actually, there's a surprising connection to everything I'm talking about. So maybe I'll mention it later on. Anyway, this is the way.
These are generated by you?
Well, by an AI.
Oh, okay.
Yeah, by DALL-E 2. Maybe I should give credit. I don't know. So yeah, this is a translation of Monge's original problem, but now we can phrase it in more mathematical terms, and this leads to the problem of optimal mass transport. Okay, so to put it in a mathematical framework, we have our pile of sand. Let's model it as a probability measure, so it has unit mass, it's normalized. And this is new, this is the source measure. We have a target probability measure. This is the hole in the ground which we need to fill. This is mu, the target measure. And we are looking for a map T, which transports nu to mu, and I'll say exactly what I mean by transport in a minute. But we also have a cost. Okay, so the cost of moving a pile of a particle of sand from position X to position Y, for now, or what we'll do, we'll measure the cost of this movement by the normed squared. So the distance between X and Y squared. In Monge's problem, the square did not exist, but somehow it leads to a nicer theory. Okay, so that's the cost of moving from X to Y, and we are looking for a map which minimizes this cost. And now there's another part of the problem which is somehow orthogonal to it, is at least for what will come next. We like to think about the source measure as being very structured or very simple in some sense. Okay, while the target measure is somehow more arbitrary or more wild. And somehow the philosophy is to study complex objects in terms of the mapping into them. So we want to study this complex measure in terms of a very simple measure and maybe a mapping. Okay. So now what do I mean by a map which transports mu to mu? Basically, I just mean that mu, the target measure, is the push forward of the source measure nu by t. Okay, in a probabilistic notation, this means that if I have a random vector nu, x, which is distributed according to nu, and I apply the map t to it, then t of x has the distribution of mu, the target. Or if I have any measurable set, I can pull it back along t and get the push forward measure. Okay, and well, if both nu and mu are nice measures in the sense that they have densities, and t is nice, then I can write the density of mu, the target, in terms of the density of nu and this transport map, right? This is the substitution of variable equation, and in this context, it is also called the Monge-Ampère equation. Just I think about t as the unknown here, and I'm trying to solve this equation. So this gives a definition of a transport map. And now, what is optimal transport? Among all maps which push forward nu to mu, I'm looking for the map, or well, a map a priori, which minimizes this energy. And basically, this is the cost of moving, right? This is the cost of moving from position x to wherever the map sends you, when you integrate over the measure nu, when you integrate over the source measure. Okay, so when we sum over all particles of sun, this is the cost of moving all particles. And then we're looking for the map which minimizes this energy. So, you know, if this is the first time you see this problem, then two things may not be clear. Maybe this is not really well defined. I mean, maybe there is no unique minimizer, but you know, maybe this set of maps could be empty, and maybe there are no transport maps. So it doesn't make sense to talk about the optimal one. Okay, maybe this is an ill-posed optimization problem. And I mean, this problem really goes back to Monge in the 1800s, and I'm going to skip about 200 years, well, into Monge's future, and give a very nice characterization of this optimal transport problem. And this is due to Brenier in the 80s. Okay, it's almost a bit more than 200 years after Monge, and later generalized by Mecan in the 90s, and they basically proved that if you have reasonable measures, mu and nu, and reasonable mostly means non-atomic, then, well, this optimization problem makes sense. There exists transport maps. There is actually an abundance of transport maps, and there exists a unique optimal transport map which achieves this minimum here, right? So, which minimizes the cost. And well, it's their theorem, their result is it goes more than an existence statement. It's actually a structural result. It tells you that not only does this map exist, it has a very, very unique form. It is always the gradient of a convex function. Okay, it is always of the form of a gradient of a convex function. And just this fact that you know that it has a very unique form, this has many applications and implications, and I mean, it is useful today in learning theory, and it is used for many things. I won't touch almost any of that, but I want to focus on one particular implication of this fact. And I mean, the fact that you know that it is a gradient of a convex function makes it interact very well with specific types of measures. Okay, measures which have some inherent form of convexity in them. And okay, this philosophy was somehow capitalized on by Caffarelli about 15 years after Brenier. And while Brenier's and McCann theorem, it's a very general theorem. Okay, it holds, you know, in vast generality almost for all measures, which satisfy really the minimal assumptions. Caffarelli really restricted himself to a very particular source measure, which is the standard Gaussian. Okay, so the standard Gaussian, it's the exponent of a quadratic form. And that's a very particular choice of the source measure. And he allowed the target measure to be slightly more arbitrary than the Gaussian, but still very much restricted. And those are measures which are called strongly log concave. Okay, so a strongly log concave measure, it's a measure which has a density with respect to the standard Gaussian. So e to the negative w is its density with respect to the standard Gaussian. And it is assumed that w is convex. Okay, so this is called a strongly log concave measure because when you add the Gaussian here, you get basically w plus a quadratic function. So you're getting a function which is strongly convex. Okay, so both those measures has some form of inherent convexity, and then in this particular case, Caffarelli proved that, you know, not only does the optimal transport map exist, it is a contraction. So it is a globally Lipschitz with Lipschitz constant 1. And to get one particular example of a strongly log concave measure, you can think about the standard Gaussian, what we have here. Think about a convex set, say an ellipsoid, condition the standard Gaussian to be on that convex set, and that's a prototypical example of a strongly log concave measure. And then Caffarelli result tells you that conditioning the standard Gaussian on a convex set is equivalent to contracting it to the set, which makes a lot of sense when you think about it, but it might be surprising when you realize that this is a very Gaussian feature. So for most measures, when you condition them on smaller sets, it's not true that this conditioning can be realized by a contraction. Basically, it's only true for Gaussian and Gaussian-like measures. Okay, and then some of this captures the convexity of the Gaussian potential. Okay, so this is somehow the introduction about mass transport, and this is a Lipschitz map transport map, Lipschitz mass transport map. And somehow what I want to focus on today is, you know, how can we extend Caffarelli's result beyond the standard Gaussian and beyond the strongly log concave measures? But maybe before I do that, I should somehow convince you that, you know, there's a reason to care about Lipschitz mappings. So actually, there are many things you can do with Lipschitz maps. I'll just want to focus on two applications. The first one is rather straightforward. It's a transference principle for functional inequalities. Okay, so here is a very basic result about the Gaussian measure. I think it goes back to Nash in the 50s. In case they couldn't find an earlier result, an earlier reference, but definitely similar stuff were known like even before Nash. And this is a form of concentration of measure. It tells you that if you take any test function f and you measure the variance of f with respect to the standard Gaussian, here f bar is the Gaussian mean of f, then this variance is always bounded from above by the fluctuations of f, and here fluctuations are measured by the squared norm, or the integral of the squared norm of the gradient of f with respect to the standard Gaussian. Okay, and somehow the moral of the story, if you have a function with small fluctuations in Gaussian space, in the sense that its gradient is small, then it behaves like a constant function. in the sense that its variance is small. And again, this is a form of concentration of measuring. It is a Gaussian-like property. It's not true for all measures. And let's see what we can do now if we know that any given measure is the push forward of the standard Gaussian by a Lipschitz map. So I claim that mu will also satisfy a similar inequality, what is called the Poincare inequality, maybe with a different constant. Right, so I want to take a test function. I want to measure its variance with respect to mu. But then I can write mu as the push forward of the standard Gaussian. So I need just to compose by the map T, the transport map T. But for the Gaussian, we know we have this Poincare inequality, so we just need to plug in instead of f composed with T and use the Gaussian Poincare inequality. And here we have a gradient of a composition, so we can just use the chain rule and factor T outside. But T is assumed to be Lipschitz, so this is bounded globally by L squared. We can simply push it outside of the integral. And again, T is a transport map, so we can go back from the standard Gaussian to the measure mu. And we get that the variance of f with respect to mu is bounded by the square norm of its gradient with respect to mu up to a constant of which is L squared. And when we take this somewhat simple argument and we combine it with Caffarelli's result, which tells you that for strongly log concave measure, you have a globally Lipschitz with constant 1 transport map, you get that every strongly log concave measure satisfies this same Poincare inequality as the standard Gaussian. So it's a two-line proof of this fact, which was originally proven, with a very complicated proof by Braskamp and Lieb in the 70s, and later by Bakri Amri with their calculus framework, with their gamma calculus, and there have been many other proofs over the years, but this is really a two-line proof, modulo Caffarelli's result. And the same argument works for a host of other functional inequalities, just not Poincare. We can also do it for log Sobolev and isoperimetric inequalities and many other types of inequalities. So again, the idea is that you can realize a somewhat arbitrary measure by a very structured measure like the standard Gaussian and a map which has nice analytic properties. In this case, Lipschitz mappings. Let's see another application. So this is more related to the central limit theorem and normal approximations. Okay, so in this setting, again, we have mu, which is the push forward of the standard Gaussian by an L Lipschitz map. And now let's say that we'll take n independent copies of mu. So this is what you do in the central limit theorem. You take independent copies of a given measure, you convolve them, you add the random vectors together, and you normalize by 1 over the square root of n, just to keep the variance constant. Right? So that's the usual thing in the central limit theorem. And now it turns out that you can bound the distance, and distance here can be Wasserstein or total variation or entropy or basically whatever. You can bound the distance of this convolved measure of what you get in the central limit theorem to a Gaussian measure at a rate. So you can bound the rate of convergence, and you get 1 over the square root of n, which is usually what you get in the central limit theorem, but you get a dependence which depends on the dimension of the square root. And usually for the central limit theorem, you get dependence which looks, well, super linear. Usually it's quadratic or cubic. And somehow just by this fact that you can realize a measure as a push forward of the Gaussian, you can get a real boost to the convergence rate in the central limit theorem in the sense of how we depend on the dimension. And here square root of d is actually optimal for most of those distances. So you just need to pay for the convergence in the Lipschitz constant. Okay, somehow the idea is that if you started from the Gaussian and you use a Lipschitz map, you cannot change your shape too much. So you still need to look like a Gaussian. Unlike the functional inequalities application, I can't really prove it in one slide, but I can try to give some intuition. And the intuition for why this normal approximation result holds is, well, it's another type of Poincare inequality. It's called the second order Poincare inequality of Shurav-Chatterjee from 2012. And again, under the same setting, if mu is the push forward of the standard Gaussian, right? So just a single summand, then he can bound the distance of mu to a Gaussian by something which only depends on the second derivative of the transport map T. Okay, so that's the second derivative of the transport map. And somehow the idea here is very similar to the Poincare inequality, is if you have a map whose gradient is small, in the sense that the Hessian has a small Gaussian norm, then it behaves like a linear function. And a linear mapping of a Gaussian is also a Gaussian. Okay, so for example, if the Hessian is 0, if this is 0, then the distance must be 0 because you're a linear mapping of the Gaussian. This is a quantitative result. But the point is that this is a second order condition, right? Because it says something about the Hessian, and Lipschitzness is a first order condition. And the idea is simply that when you convolve things in the central limit theorem, then you get regularity. So you can upgrade second order conditions into first order conditions. Feel free to stop me at any point if you have questions. All right, so given these applications, one question which we can ask now is, okay, which measures can be realized with the push forward of the standard Gaussian by a Lipschitz map? So we know one class of measures, which are those which are strongly log concave. And there have been several extensions of Caffarelli's result, but most of them are very restricted. Okay, so the first one is due to Kolesnikov, and he considered the following case. You have a log concave measure. So again, W is convex here, but now it's the density with respect to the Lebesgue measure, not with respect to the standard Gaussian, so it's a weaker condition. But the measure is assumed to have bounded support, so it's supported on a ball of radius r. And then Kolesnikov showed that there is a Lipschitz constant, there is a Lipschitz map from the standard Gaussian to those types of measure with a Lipschitz constant which depends on the size of the support, but also on the dimension. So it depends at square root of the dimension. And a priori, there should be no reason for the dimensional dependence to kick in here. And if you think about the previous examples, we really like the fact that at least in Caffarelli's result, the Lipschitz constant was dimension independent. It was just one. Right? So for example, in the central limit theorem, you're going to lose something with respect to the dimension, which is maybe not what you want. And another result is due to Colombo, Figali, and Javeri, and they considered bounded perturbations. So you take the Gaussian measure and you perturb it by some density, and here W doesn't need to be convex, just bounded. And under some conditions, which I won't mention, they get dimension independent Lipschitz constant to those measures, which really has a bad dependence on this parameter M. It's double exponential in M. And basically those are the only, at least results I know, which extend Caffarelli's result. And somehow the reason is that it is very hard to reason about the Monge-Ampere equation. Somehow, because the optimal transport map was the gradient of a convex function, and all those convexity conditions merged together, Caffarelli managed to give a very substantial result. But in general, it's hard to reason. It's a very nonlinear PDE, so it's very hard to deduce facts about it. So somehow it makes sense to, if you want to prove those applications, if you have to prove those things they've seen, it somehow makes sense to not look at the optimal transport map. Maybe to look at transport map, which can be proven to be Lipschitz, but that don't necessarily need to be the optimal transport map. And there's another evidence for that, and this is an example we've recently found, is that the Lipschitz constant of the optimal transport map, which is what Caffarelli used, can be arbitrarily worse than the best Lipschitz constant achieved by some map. And the example is basically, well, this picture. Think about two ellipsoids. You want to transport this ellipsoid to this ellipsoid. Now there's a rigid motion which does it. You can simply rotate it. So there's an isometry to do it. But what the optimal transport map would try to do, well, it wants to minimize distances. So it will try to squeeze one dimension, and then it will try to, well, squeeze in the other direction to stretch the other dimension. So there is an isometry which transports one to the other, yet the optimal transport map will elongate distances. So somehow the idea is to look for transport maps, and this is what I want to talk about now, for Lipschitz transport maps, which are not necessarily the optimal transport. And then maybe we can have a better way to analyze the Lipschitz constant, and we have more flexibility in this search. Okay, so what I'll do from now on, I'll mention some results we have. So one is an extension of Caffarelli's theorem with a different transport map in Euclidean spaces. And then I'll talk about a corresponding result which goes beyond Euclidean spaces and in Riemannian manifolds. And if I have some time at the end, maybe I'll speak a bit about the technical details. Okay. So let's say something about Euclidean spaces.
Sorry, Dan, can you
Yeah.
go back to slides? So you were talking about this example. Can you explain a little more? What do you exactly mean? What is the goal essentially?
So yeah, think about the without getting into too much details, because what I'm going to say is not true, but at least ideologically, think about the uniform measure on an ellipsoid, which is, has one long direction and one short direction. And think about the uniform measure on its rotation.
Okay.
So you can transport one to the other simply by a rotation.
Yes.
But the optimal transport map would want to conserve distances.
Right.
So a rotation may be bad for you, and it might be easier to just stretch the dimensions. So you are going to change stuff. So you are going to stretch at least one dimension.
Right.
And the actual example doesn't really work with ellipsoids, but with Gaussians, which are not non-standard Gauss or non-isotropic Gaussians.
Okay.
But somehow those ellipsoids kind of capture the idea. And the picture is cool.
Sure.
Thanks, Dali. Right. So what did we manage to do in Euclidean spaces? And that's a joint paper with Yair Schenfeld, who is also at MIT. And well, we proved that if the source measure is reasonable, and reasonable here basically is in the same sense of Brenian and McCann. Sorry, if the target measure is reasonable, then there exists a transport map which pushes forward the standard Gaussian to this measure mu. So up to now I've said nothing, because this is also true for the optimal transport map. But we can also prove that T is Lipschitz in several different cases. One is when mu is low concave with compact supports, which is the same thing that Kolesnikov showed, but he had a non-optimal Lipschitz constant, which depended on the dimension. Here we managed to prove the optimal constant with no dimension dependence. Also, when mu is a bounded perturbation of the Gaussian, again, in the sense of Colombo, Figali, and Javeri, and where they get this double exponential. So we managed to get the correct constant, which is a single exponential, but we can also prove it for other cases. So for example, if mu is a Gaussian mixture, or at least some form of a Gaussian mixture, so we can show that a rather large class of Gaussian mixtures can be realized as the push forward of the standard Gaussian by a Lipschitz map. And also some other cases, for example, measures which are not necessarily log concave, but maybe their Hessian can be negative, just bounded from below, and things like that. Okay, and so all of those results are sharp in the Lipschitz constant they achieve, and they improve many results in the literature. So I've mentioned the results of Kolesnikov and Colombo, Figali, Javeri, but also from the applications. So for example, it improves many known functional inequalities, both for Gaussian mixtures and for log concave measures. And maybe as a comment, the results are not restricted to Gaussian. So you don't really need to have the Gaussian here as the source measure. There is some flexibility. So instead of actually, proving it now and speaking about the detail, what I want to do is to give a general recipe on how to construct a transport map. And then I'll explain how to analyze its Lipschitz constant. And maybe towards the end, I'll say something about, how do we actually manifest this recipe. So it's a recipe in 3 steps and basically 3 tautologies, but somehow you get something out of those tautologies. And in the first step, you have 2 measures. You have your source measure nu and your target measure mu. And well, somehow you want to take this static problem of transport. You have 2 measures which are static. You want to transport one to the other. You want to make it into a dynamic problem. So you want to interpolate them using a flow of measures. Okay, so you have a measure valued path, rho t, of probability measures, which at time 0 is your target, is your source, and at time infinity is your target. But at any intermediate time, it is some probability measure. Okay, so whatever, you can do it, you can realize it in infinitely many ways, but you want to find a nice flow of measure, which has some nice regularity properties, at least, which I won't get into. But now here is the crucial point. If you have a flow of measures and you're interpolating between 2 probability measures, then mass is conserved along the flow. Because you have unit mass, and at each time of the flow, you are conserving the fact that you have a unit mass. So you have a conservation of mass law, okay? Which means that the dynamics of this flow are governed by a PDE, which is sometimes called the continuity equation. Okay, here, right, rho t, think about it as the density of the, I'm identifying rho t with its density for simplicity, and the time dynamics of rho t, well, they're determined by some vector field, vt, which can depend on time. So here vt is a vector field which goes from the space to itself, and you just multiply it by the measure rho t, and you're taking the gradient. Some of this PDE, because you have a conservation of mass law, it controls the dynamics. So that's another, just a different point of view on the same object. Somehow you can, it's not a bijection, but you can fit a vector field to any such interpolation. But this is once we have those dynamics for the entire mass, well, we can ask what happens to a single particle of sand, right? We can contrast the Eulerian point of view and the Lagrangian point of view, right? Those are the dynamics of the entire mass. And you can ask, if we focus on a single particle of sand, where does this particle go to? So in this, when we think about this perspective, we get another sort of PDA that's an integral curve equation. Here, T is the unknown, right? But T is a map which tells you if you started at position X along those dynamics, where are you going to end up at point T, right? If we think about a probability measure which models, a pile of sand, we want to ask for each single particle where it will be at time T, and this is the following equation. And the way to connect between the Eulerian and the Lagrangian point of view here is that you have this vector field V, and this is the vector field which appears here in the integral curve equation. And the way to connect it back into the flow of measures is that if you take the solution to this equation, it's a map, basically it's a flow of maps, then it encodes the flow of measures by the fact that at time T, the map T of T pushes forward the initial measure, rho 0, to the measure at time T, rho T. So if you have this for every T, you can take the limit as lowercase t approaches infinity, and you get a map which pushes forward the origin, the source measure, to the terminal point, to the target measure. All right, so I'm basically giving here three perspectives on the same construction, but the idea here is that I can start by finding a flow of measures. I can use it to find a vector field which gives the continuity equation, and then I can use the vector field to construct a map. So even though those are three equivalent perspectives, I, as an algorithm, as a recipe, can start from one side and end at the other side. And if I know I have a map which solves this integral curve equation, its Lipschitz constant becomes somewhat accessible, right? Because what is the Lipschitz constant? I just want to take a derivative here. I want to bound the gradient of the map. So, you can just take the spatial derivative on the left side, and it commutes with the time derivative. And we can also take the spatial gradient on the right-hand side and just apply the chain rule, right? And what we get here is that the dynamics of the gradient, they are equal to, now it's some matrix times the gradient. And we want to bound this from above, right? So in a perfect world, we would divide both sides by the gradient of t. And here we have the time derivative of the gradient over the gradient. So it's the logarithmic derivative, and then we can just exponentiate and integrate. Integrate and exponentiate. And this actually, works just this way in dimension 1. In higher dimensions, you need to say something because you can't really divide by the gradient, but still the same principle works. Right? So you need to integrate and exponentiate, and then you can bound the Lipschitz constant of this map T, of the limit map, as what happens when you integrate the maximal singular value of this map here, and you exponentiate. Right? So you can start with a flow of measures. You can find this vector field V, and now you just need to find its maximal singular value and integrate it and exponentiate. And if you've managed to find a nice flow of measures, then you manage to find a map which has a nice Lipschitz constant. I mean, it's not always doable, but when you can do it, this is one way to do it. And in the proof of our theorem, we interpolate, or our choice of interpolation is using the Langevin dynamics. So it's an Ito process, and somehow it gives rise to an interpolation between laws. All right. So yeah, that's what I wanted to say about the Euclidean case. I want to say something else about Riemannian manifolds. So somehow the point is that for Riemannian manifold, there is no analog of Caffarelli's results, and I'll show that in a second, but really much less is known about mass transport in general, but in particular about Lipschitz mass transport. So I can summarize everything we know about Lipschitz transport map in the next half slide. Right, so, so I see a question in the chat. Any specific reason for using the continuity equation? So somehow the continuity equation is not really, yeah, I really don't care about the continuity equation, but somehow if I have a flow of measures, it's somehow more convenient to find the form for this vector field from the continuity equation and then use it to construct those maps. So the way we do it, we look at the flow, we solve the continuity equation, then we solve the integral curve equation to get this vector field. In theory, this is a redundant step. We don't really need it, but I don't really know how to find this vector field without looking at the continuity equation. I hope this answers the question. Right. So I think that so there are many choices here for the vector field once you have an interpolation, and I really didn't say, and there's really no one way to actually write the continuity equation. Right. So for example, if I add here any vector field with curl 0, I would get the same equation. But the point here is that when you have an Ito process, then this reduces to the Fokker-Planck equation, which is really easy to understand. Well, at least it's accessible. But definitely you could look at other sorts of dynamics.
People can unmute themselves and ask questions. They don't need to put it on the chat, but yeah, sure. Go ahead, Dan.
Okay.
I have a question. Isn't the continuity equation not required for mass conservation?
Sorry, I couldn't hear one.
Isn't the continuity equation not required for mass conservation?
It's required for mass conservation. I mean, once you have a mass conservation, you get a continuity equation, right?
Yes. So we start with the source and our target measures are of the same mass. So
yes,
the interpolant masses should also be. It's a natural choice to have the interpolant masses to also have the same mass.
That's a good question. I mean, it's once we've normalized the source and the target to be probability measures, it is. So that's an opinion now, but I think it is somehow natural to take an interpolant, which is also a probability measure, and but in theory. In theory, it's not required, and definitely, if you want to transport a small amount of mass into a large amount of mass, it's not something you could do, right? If you want to do a partial transport.
Okay, I get it. Yes, thank you.
Thanks for the question. Okay, so here is what we know about mass transport in Riemannian manifolds. So in the setting, you have a compact Riemannian manifold and a compact manifold M and a Riemannian metric D. And you can define the same optimal transport problem as in the Euclidean case. The only difference is that, well, except of taking the Euclidean distance squared, you're taking the Riemannian distance squared. Otherwise, it's the exact same problem. And McCann proved in 2001 that just like in the Euclidean case, there is a unique optimal transport map, which is given as a gradient of some function which satisfies some notion of convexity. So that's the exact analog. It's of the Euclidean case. It's a generalization, except for the fact that M is a compact manifold. And he also had the following result in his paper, is that if both measures have full support, so they're supported on the entire manifold, sorry, then the optimal transport map is Lipschitz. But it's a non-quantitative result. So just think about it, that you have a map between two compact spaces. It's a continuous map, and then Caffarelli tells you, okay, it's slightly better than continuous, it's Lipschitz. But, sorry, not Caffarelli, McCann. It's slightly better than continuous, it's Lipschitz, but the Lipschitz constant a priori could be anything. Okay, so it's not a very informative statement. It's more of a qualitative statement. And you know, this kind of leaves the question: is there an analog of Caffarelli theorem for manifolds? So as I said, no. And here is the example, or an example. So the nicest Riemannian manifold I can think about is the round sphere. And the nicest measure on the round sphere is just the uniform measure, the uniform probability measure. And so that will be the target. Sorry, that will be the source. And as the target, we can take the uniform measure on a hemisphere. And now we can ask whether we can transport the uniform measure on the entire sphere to the uniform measure on a hemisphere in a Lipschitz way. And well, the optimal transport map will not work. This is what you get in Caffarelli's theorem. It will not work because try to think about where will you take the North Pole, right? You want to minimize the distance it moves, so it must move to the equator, but by symmetry, there is no continuous way to do it. So the optimal transport map, it exists, but it's not even continuous, so it's not Lipschitz. On the other hand, on this case, you have a very easy Lipschitz map. You can simply fold the sphere, right, or push it inside, depends on how you want to think about it. So again, it tells you that the optimal transport map really is not the correct object you want to look at. In general, when you have non-flat spaces, or rather spaces which have some topological abstractions. And what can we do on Riemannian manifolds now? So what would be a natural condition for the existence of a Lipschitz transport map, right? Because when we think about it here, this is the exact analog of what I said before. We have the uniform measure on the sphere, which is the analog of the Gaussian in Euclidean space, and we are simply restricting it to a smaller convex subset. So this is the exact analog of where Caffarelli's result holds, and here somehow doesn't really work. And what would be a natural condition? So we can think about several different things, maybe strongly log concave functions, except it doesn't really work because on a compact manifold, there are no convex functions, not geodesically convex functions at least. And you can think about measures which are supported on a smaller set, like we had log concave with bounded support in Euclidean case. But again, this causes some topological obstructions. And well, in Euclidean spaces, we had mixtures of Gaussians, but if you take a mixture of a Haar measure on a sphere, it doesn't matter how you do it, it would be trivial. So those are not interesting. And what we actually did, we identified a metric condition on Riemannian manifold, and this is the following condition. We take we take the source measure to be a perturbation of the source. So it has a density e to the negative w. And we assume that W is a Lipschitz function. This is what we call a log Lipschitz perturbation. Okay, and I call this a metric condition because the definition of being Lipschitz on a Riemannian manifold, it depends on the metric. So somehow it's desirable. You want those conditions to be compatible with the spaces you work in. Right, but now we have two sources of Lipschitzness. One is in the density, and one comes from the transport map. And this is a theorem we proved, again, together with Erich Scheinfeld, but also with Max Fati, who is in a university in Paris. And if we have two measures on a Riemannian manifold, doesn't have to be compact, and we assume that the manifold plus the source measure satisfies some curvature assumption condition, which I won't get into it. It involves the Ricci curvature and the Hessian of the measure. But as an example, you can think about the round sphere. So the round sphere satisfies this condition, but somehow it is a condition of positively curved manifolds. And if we assume that the target measure mu is a log Lipschitz perturbation with constant L, okay, so this is an L Lipschitz function, then we get a transport map with a Lipschitz constant, which depends exponentially on L, or exponentially on L squared, and double exponentially on basically curvature terms. So this Riemannian infinity norm depends on many curvature terms. It depends on the gradient of the Ricci curvature and on many other things. And it's not clear if this is a necessary thing. But at least in two specific cases, we know how to, we can show that this is not necessary, that the curvature term do not need to appear. One is a trivial case when the manifold is flat, in RD. So this just disappears. But also for the round sphere, this term just disappears and we get something which only depends exponentially on L. And in those cases, we can show that this is an optimal result. This is the best Lipschitz constant you could hope for. And in other cases, we simply don't know at the moment. But it already leads to new results in RD. So we can prove new types of functional inequalities for Lipschitz perturbation of the Gaussian. And somehow that's a nice result, but also on Riemannian manifold, it's pretty brand new. Right, so maybe I have just a few minutes left, so maybe I'll just say one word about how we construct the two maps here. What is the interpolation of measures we choose, and then I'll stop. Right, so we use the Langevin dynamics. As I said before, it's an Ito process, which is defined in the following way. If we have our source nu, and we have the target mu, well, we construct the following Ito process, which at time 0, it starts from the target, and it evolves according to those dynamics. Here, W of nu is just the potential of the measure nu. Right? So you take a Brownian motion, but you somehow shape it. Its drift depends only on the gradient of this function W of nu. So you keep pushing it in those directions, and it turns out that, well, with some pretty restrictive regularity assumption, but which work in many cases, this Ito process is a unique invariant measure, and it is given by nu. So if you define the measure of the process at time t, you get an interpolation of measure, such that at the beginning, at time 0, you start at the target, and at time infinity, you converge to the source. Right? And so you basically reverse time, because the idea is that you can encode the niceness properties of the source, think about the Gaussian, in the process here. Right? So for example, for the Gaussian, this just reduces to the Orenstein-Uhlenbeck process. So because the target is more arbitrary, this process might not be as nice. So we basically interpolate from the target to the source, and then we reverse time. And sorry?
No, please go on.
Oh, okay. And somehow we can get a very clear expression for the vector field in the continuity equation, and it is just given by some semi-group which applies on the relative density. Okay, very, very vague, but this is what we call the Langevin transport map. So it only depends on this semi-group acting on the, well, the Lipschitz constant only depends on this semi-group, which acts on the relative density. And then all of those results, they just find different ways to bound basically this thing. So in Euclidean cases, we can do very simple things. We somehow, at least with respect to the standard Gaussian, the semi-group is just a convolution kernel with a Gaussian kernel. Somehow this thing reduces to a positive definite matrix, and you know, whatever, we have some covariance inequalities, and we do it. In a Riemannian manifold, the story is a bit more complicated, right? Because instead of using a standard Brownian motion, we use a Brownian motion on the manifold, but there is no covariance representation, and we need to do some more you know, complicated stuff. Basically, everything reduces to what's called a bismuth formula. So it's an integration by parts formula in the space of paths. Okay, yeah, this was very, very vague, but yeah, that's what I could say in 2 minutes. But maybe in the last minute, I'll just say about future direction. So one interesting question is to further expand the results on a Riemannian manifold. For example, there is a very, very basic question of Beck and Jerison, which asks the following. Basically, where I showed that the optimal transport map fails if you have the uniform measure on the sphere, and you have the uniform measure on a geodesically convex set. Can you realize one by the other by a Lipschitz map? And the same thing that Caffarelli does in the Euclidean spaces. This is completely open, you know, and it's a very basic question. Another direction would be to think about a more structured theory of optimal Lipschitz mappings. For example, in optimal transport, you try to minimize distances, but maybe instead of minimizing distances, you can just try to minimize the Lipschitz constant, you know, by force, not to find an ad hoc construction, but to find an optimization problem whose solution is a transport map with the optimal Lipschitz constant. Currently, I mean, this is a tough, like the Lipschitz constant is a very it's a very L infinity quantity, so it's very hard to work with. It's not clear how to define the problem, but we know how to define it for proxies. So instead of working with Lipschitz constant, we can know how to do it for optimizing Sobolev norms, and somehow in some cases we can show that there is a unique mapping, but you know, we don't have any structural theorem for it. And another thing which is highly relevant, apparently, is efficiently computable mappings, right? So the point is this Langevin map, this vector field, you can express the map using the vector field, but in most cases there is no efficient algorithm to compute it or to approximate it. And this is even more true for the optimal transport map, where the map is a solution of a very nonlinear PD. So, you know, forget about Lipschitz mappings. Can we even, you know, find other types of interpolations for which the vector field is efficiently computable? And this is a very relevant question, because here is something I just learned recently. So this map we use here, and we call the Langevin transport map, which basically interpolates using the Langevin dynamics. This is what those diffusion models, you know, do for generating all of the artificially generated images I have on my slides. They interpolate a measure on images with noise, and then they really use a neural network to approximate that map in a very, very concrete sense. So somehow finding something which is more efficiently computable can lead to a better theory of those generative models. I mean, that makes sense to look at least. Okay, that's all I wanted to say. Thank you for listening.
Let's thank Dan for his wonderful talk.
Sir, I had a few questions. Is it?
Yes.
Can I? Yeah. So we actually have to define Brownian motions or stochastic processes on manifolds. We make use of Schwarz morphisms, and we can actually have a Statanovich representation of a stochastic process on a Riemannian manifold and convert it into Ito process back and forth. As long as we have a connection on a, I mean, since it is Riemannian, we already have a connection, so that's not a problem. So we can actually go from Statanovich to Ito, and
Yes.
and we can do the analysis in the mean sense in the Ito processes. So my question is, like, what's the reason to go for Bismuth formula? That's the first question. And the other question is, when we talk about Ito processes, we always have to take care of the second order derivative. So the continuity equation was not making sense because when we convert an Euler equation, let's say we start with an Euler equation and we want to find a characteristic of an Euler equation. Like we I mean, we will actually get a Lagrangian version of it. But when we try to do the same for, let's say, Berger's equation, we have to make use of Ito Wenzel's formula and think of the characteristic as a stochastic process. So in this case, since we are using continuity equation, we will not have the second order term. So using stochastic process is also another question which I am not able to understand. Yeah.
Okay, so I think there were several questions. Maybe I'll start with the first one. So about Ito versus Stefanovic. So maybe I'm not being very fair here. So I represent it as an Ito process because I'm used to Ito processes, but there's no special reason. We don't really use Ito calculus. Okay, so Bismuth formula is a formula on the space of paths. So it doesn't matter if you represent your process as an Ito process or a Stefanovic process. It's just it allows you to reduce derivatives. So it's not Ito calculus, it's a Maliavin calculus, if that makes sense. So the distinction between Ito and Stefanovic doesn't really play a part, at least not for me here. Now, about the continuity equation, and then remind me if I forgot to speak about something. Right, so about the continuity equation, for an Ito process, it is just the Fokker-Planck equation or the forward-Kolmogorov equation. I mean, the Fokker-Planck equation satisfies the continuity equation. If you take the how do you call it? The volatility parameter squared, this and take the antiderivative, this will give you the vector field V. So somehow you get this derivative from here. I'm not sure if that answers your question.
But the Fokker-Planck equation will normally have the second order term, but the continuity equation here doesn't have that. That's my only concern.
Oh, right, but I mean somehow this vector field encodes for the second order term, right? Because right, you can see that it is a gradient of something. This is usually the case. Okay, here it is. It is the gradient of something, and then you are taking the gradient in the continuity equation, so you get a second order term. Although here it is the time reversal of the Ito process, but still you get a second order term. Right, so the vector field itself will be a derivative. Yes, am I answering the correct question?
Yeah.
Other questions from the audience?
Yeah, I have one more question. So when we look at mechanics, we have like, you know, when we talk about calculus of variation, and we have its equivalent version, which tells us that we can, like, I mean, the integral of Lagrangian, that's the action, and the minimal action gives us the geodesic over a manifold. So can we think of something similar in case of say stochastic processes, and try to relate it to optimal transport?
Yeah, that's a very good question. Okay.
And also as an addendum to this question, do you think it is possible for us to have a Hamiltonian version, let's say on a cotangent bundle for the so that the base is, I mean, what I'm trying to say is, let's say we have a flow, we get a flow on the tangent bundle, and can we have a dual of it, like, you know,
Yes,
like,
yes.
say by using Legendre transform or something like that on the cotangent bundle? If so, can we start with a function right from the cotangent bundle itself and try to have an optimal flow just by choosing a function?
Yes, that's a good question. Okay, so let me start with, okay, I'm not sure, I haven't thought about the second question, but let me say something about the first question. I mean, is there some sense of minimal action with Ito process? Oh, no, not with Ito processes, with stochastic processes.
Yeah.
So, I mean, here is, again, a tautology. If you go to this recipe here, and you can realize the optimal transport map simply by, I mean, taking the optimal transport map and interpolating linearly between the optimal transport map and the identity. So this will give you a flow of measures along that. It's very, very non-stochastic, right? It's very deterministic in that sense. It's not a stochastic, it's not a stochastic process, but you can realize it in the space of paths, for example, and then you will move in straight lines from the starting position to the end position. That's not a very satisfying answer, but there is a way to define a stochastic process which essentially adds noise to this construction. Okay, so maybe I'll go to the optimal. Yeah, here is the optimal transport problem. So you can regularize it by, say, adding an entropy term. So you want to minimize distance, but at the same time, you want to minimize, you get a coupling here. Right, the idea is not to minimize now over maps, but to minimize over couplings. Right, every map induces a coupling, but not every coupling is supported on the graph of a function. So you can minimize it over coupling, and now you want to regularize by the entropy of the coupling you get with respect to the, say, product measure between the source and the target. Now, if you think about it, if you add this regularization term and you get an optimal coupling, it cannot be deterministic. It cannot be supported on the graph of a function, because if you have a coupling which is given by a map, it is singular in the product space. So it will have an infinite entropy with respect to the product measure. So you will get something random. Now, several things turn out to be true. It turns out that this random thing can be realized as an Ito process. Sorry, not as an Ito process, as a stochastic process. This is called the Schrödinger bridge. And it is an interpolation between the source and the target. And if you look at the path of the Schrödinger bridge, if you take the regularization term to 0, and which is equivalent to basically taking the noise to 0, those random paths will converge to the path of the optimal transport function. So this is somehow an optimal way to construct an interpolating process. I mean, in the limit at least. And this is actually a very useful idea because it turns out that those entropy regularized processes are efficiently computable. So they don't give you a map, but they give you some approximation of the map. So that's a very nice thing to have. About the other question you asked, yeah, I haven't thought about it. So yeah, I'm sorry, I don't have anything smart to say.
So you mean to say in the EOT, in the entropy or optimal transport, the joint measure, that is a coupling, is going to be not supported on a lower dimensional space?
It cannot be supported on a lower dimension. I mean, if
I
your
see.
two measures are non-singular, then the EOT cannot be supported on a lower dimensional space.
Oh, lovely. I see. Okay.
Right, simply
So then
because
there is a, yeah, I understand. So then the parameter epsilon that they often introduce in the EOT, which is the coefficient of the Kullback-Leibler.
regularized.
So that basically is like playing the role of a regularizer. So it's controlling. Yes. Oh, I see. I see. Thank you.
Yes.
So then, one can actually prove like certain regularity related results by letting that parameter go to zero. Is that is that too much of a leap of faith?
So, in theory, yes. In theory, yes. In practice, things usually blow up when you take the parameter to zero. So I actually don't know many results which actually do take the parameter to zero. For example, the approximation you can get for the coupling really, blows up when you take the parameter to zero. But one nice thing I know is there is a proof of Caffarelli's theorem which proves an analogous result for the optimal entropic regularized coupling, and then takes the parameter to zero, and somehow it works, and it doesn't work for anything else in that context.
I see. And what is that? But what is that reference? If you don't know,
I can look for it. Maybe I'll post it in the chat.
Oh, that would be great. Or you just send it to Nishant and he'll send it to me.
Okay, it will take me a minute. Caffarelli entropic. That should be it. Yeah, here it is. So that's a very, very nice. Okay, that's a very nice paper.
So when you were, I'm guessing that everybody has already left. So can we continue, Nishant? Is that okay? Or is that okay with Dan?
Yeah, I'm sure. It's
okay. Anyway. So when you were talking about the central limit theorem, basically your normalized mu(n). What happened? I think he left. Oh, okay. When you were talking about the central limit theorem, the rate for the central limit theorem, there you had your the samples were generated from mu star. Mu star was some sort of a push forward of a Gaussian.
Yes.
Why is that necessary? Why, I mean, is that necessary to have push forward of the Gaussian?
No, it's not. I mean, it's not necessary. Definitely not for the central limit theorem. No, it's not necessary. I mean, the central limit theorem holds a much larger generality. Exactly. But the point is, if you are the push forward of the Gaussian by a Lipschitz map, but it doesn't even have to be Lipschitz, by a map which has if you can bound the moments of its gradient, then you get a dimensional improvement in the central limit theorem.
I see.
So that's the point. You can somehow trade off dimensional rates of convergence in the central limit theorem for regularity of the transport map.
I see.
Yeah, the point is that usually, if you're, okay, I'm kind of making an artificial distinction here, but if your measure is not realized at the push forward of the Gaussian by a map, or at least by a Lipschitz map, then there are examples where the rate of convergence should be like d cubed, at least d cubed.
I see.
Where d is the dimension. And somehow, if you have a Lipschitz map, then you can rule out those cases. It must be square root of d. And this is optimal.
Okay. And are there any results for the like regularity of T, the transport map?
Oh, yeah, yes. Okay. So the optimal transport map, it gets regularity from both the source and the target. So if the source and the target are k times continuously differentiable,
Yeah.
then the optimal transport map is k minus 2.
Yeah. So that is Figali and Caffarelli.
Yes. And those are very deep results in PDE. Yeah.
Right. So no, in terms of entropy optimal transport, are there any regularity results from there?
Oh, I mean, so that's a good question. So you would inherit the same kind of regularity because maybe you get something which is improved because you
It should be improved, right? Because you are
it should be improved because you are integrating against a kernel.
Precisely.
So I'm not sure. I don't know, but it should be improved. I'm not sure. Maybe it should definitely be more regular than the optimal transport map. It can't be smooth in general. Yeah, I'm not sure.
See. Okay. That's okay.
But it should be improved. Yeah.
I see. Thank you. That was a very nice talk.
Thanks for the question.
Any further questions? Okay. Thanks a lot, Dan.
Thanks a lot for the invitation.